Welcome to the technical module on transmission systems and reactive power control. Today we explore the physics of overhead lines and the critical management of reactive power in high voltage grids. In this technical module, we will explore six critical domains of power systems engineering. First, we examine overhead transmission line conductor selection, including ACSR and HTLS technologies. Second, we break down sag tension calculations using the fundamental parabolic formula. Third, we analyze bundle conductors and corona loss management in EHV lines. Fourth, we compare LCC and VSC HVDC technologies. Fifth, we evaluate underground XLPE cables and their thermal ratings. Finally, we conclude with passive reactive power compensation, detailing capacitor banks and shunt reactors. In high voltage transmission, conductor selection requires a precise balance between mechanical strength and electrical conductivity. The industry baseline is ACSR, aluminum conductor steel reinforced. Let's examine its internal structure. At the center is a high strength galvanized steel core. This core provides the essential tensile strength needed to support the conductor's immense weight over long spans between towers, resisting wind and ice loads. Surrounding the steel core are multiple concentric layers of aluminum strands. While the steel handles the physical tension, these outer aluminum layers are responsible for carrying the electrical current efficiently. This composite design makes ACSR highly reliable, serving as the foundational technology in overhead grids. To increase capacity on existing transmission corridors without replacing towers, power systems engineers turn to high temperature low sag or HTLS conductors. Traditional ACSR conductors rely on a steel core, which expands significantly under high thermal loads, causing the line to sag closer to the ground. This physical thermal expansion strictly limits the maximum safe operating temperature, which in turn severely restricts the overall current carrying capacity of the transmission line. ACC technology solves this limitation by utilizing an aluminum conductor composite core, which exhibits a minimal coefficient of thermal expansion. As a result, ACCC conductors can operate at much higher temperatures, carrying significantly more current than ACSR, while maintaining safe ground clearance and lower sag. The mechanical safety and reliability of an overhead transmission line depend heavily on the sag tension relationship. When a conductor is suspended between two towers, its own weight prevents it from hanging in a perfectly straight line, forming a curve instead. We define sag as the precise vertical distance between the horizontal line of support and the lowest point of the hanging conductor. Maintaining optimal sag is critical. Excessive sag compromises safe ground clearance, risking severe electrical faults. Conversely, insufficient sag drastically increases mechanical tension, risking conductor breakage. This balance is influenced by weight, span length, and tension. For most practical transmission line spans, engineers use the parabolic approximation rather than complex catenary equations to calculate sag. This formula states that the sag, denoted as S, equals the conductor's weight per unit length, W, multiplied by the span length, L squared. This result is then divided by 8 times the horizontal tension, T, applied to the conductor. It is critical to note the exponential relationship here, because the span length L is squared. Doubling the distance between towers will quadruple the resultant sag. Conversely, increasing the horizontal tension T will linearly reduce the sag, but this places significantly higher mechanical stress on the supporting structures. In extra high voltage and ultra high voltage systems, a unique phenomenon occurs at the surface of the transmission lines. When the localized electrical voltage gradient exceeds the dielectric strength of the surrounding air, typically around 30 kilovolts per centimeter, the air molecules become ionized, creating a conductive path. This partial discharge is known as the corona effect. Visually, it appears as a faint purple glow. However, it's much more than just a visual effect. Corona leads to significant active power loss, audible hissing noise, and radio interference, especially during foul weather. To mitigate the severe coronal losses in extra high voltage and ultra high voltage lines, engineers employ bundled conductors. Instead of using one massive cable, a single phase is split into a bundle of two, four, or even six smaller subconductors. These subconductors are held apart by metallic spacers, a geometric arrangement that drastically increases the effective radius of the phase. By expanding the effective diameter, the surface voltage gradient drops significantly, preventing the surrounding air from ionizing and reducing corona discharge. As an added benefit, this configuration lowers the line's series inductance, which directly increases the power transfer capability of the grid. While overhead lines are standard, urban constraints or environmental factors often make them unfeasible, requiring a transition to high voltage underground cables. The structural core of modern underground transmission is XLPE, or cross linked polyethylene. It is a highly robust solid dielectric. Let's examine its cross sectional layers. At the center lies the conductor, surrounded by a semiconducting screen to smooth the electric field. Next comes the thick XLPE insulation layer, which serves as the critical electrical barrier. Crucially, its cross-linked molecular structure provides remarkable thermal stability, withstanding continuous operating temperatures up to 90 degrees Celsius. Finally, an insulation screen, a metallic sheath, and a protective outer jacket complete the cable. Thermal rating is the primary constraint for underground XLPE cable systems. Unlike overhead transmission lines, which are efficiently cooled by ambient air convection, underground cables rely entirely on thermal conduction through the surrounding soil. Because soil has a much higher thermal resistivity than air, heat dissipation is significantly slower. Engineers must carefully calculate this thermal bottleneck to prevent insulation degradation and strict ampacity limits. As power grids expand, transmitting bulk energy over vast distances presents a significant challenge for traditional alternating current systems. For ultra long distances or subsea applications, high voltage direct current or HVDC becomes the superior engineering choice. In long AC lines, capacitive charging currents consume transmission capacity, limiting the effective distance. Underground and subsea AC cables are especially susceptible, often capping out around 50 to 100 kilometers. HVDC eliminates these capacitive charging issues entirely. Furthermore, it acts as a firewall, allowing for precise control of power flow between non-synchronized AC networks. This capability is essential when connecting grids operating at different frequencies, forming the backbone of modern supergrids. When designing high voltage direct current systems, engineers choose between two primary converter technologies, LCC and VSC. LCC, or line commutated converters, rely on robust thyristor semiconductors. Because thyristors cannot be actively turned off, LCC requires a strong AC grid for commutation. However, LCC excels in shear capacity, remaining the standard for ultra-high power bulk transmission over extreme distances. In contrast, VSC or voltage source converters utilize insulated gate bipolar transistors or IGBTs, which can be switched independently. This grants VSC independent control of active and reactive power. Though historically lower in power rating, VSC can restart a collapsed grid, a feature known as black start. Reactive power management is a critical requirement for maintaining voltage stability across high voltage transmission networks. In AC systems, the phase angle between voltage and current dictates power flow. Under heavy inductive loads, the current wave lags behind the voltage wave. This lagging current consumes reactive power, causing a significant voltage drop along the transmission line. Conversely, during light load periods, the line's natural capacitance dominates. This generates reactive power, leading to a voltage rise at the receiving end. This is known as the Ferranti effect. Because this balance constantly shifts with demand, continuous reactive compensation is essential. In high voltage transmission networks, Shunt capacitor banks serve as the primary form of passive reactive power compensation. These units are connected directly to the system busbar through a dedicated circuit breaker, allowing them to be switched on demand. During periods of peak load, heavily loaded inductive lines consume significant reactive power, leading to localized voltage drops. By injecting leading reactive power, or VARs, precisely at the point of load, capacitor banks improve the power factor and restore the nominal voltage profile. Conversely, during light load periods, the dynamics of long transmission lines change. The line's natural capacitance dominates, generating excess reactive power. This causes the receiving end voltage to rise dangerously high, a phenomenon known as the Ferranti effect. To counteract this, grid operators deploy shunt reactors. These large inductive coils are connected in parallel to the grid to absorb the excess reactive power. By neutralizing the capacitive VARs, they pull the voltage back to safe levels. Effective grid management requires a coordinated strategy of switching passive reactive power components. As daily demand fluctuates, system voltage naturally deviates from its nominal set point. During peak loads, voltage sags toward the lower limit. Utilities switch on shunt capacitor banks to inject reactive power and boost voltage. Conversely, during light loads, the Ferranti effect causes voltage to rise. Shunt reactors are engaged to absorb excess reactive power. By dynamically balancing capacitors and reactors, utilities ensure the transmission voltage remains securely within a narrow, stable envelope. We've now covered the full spectrum of transmission physics and reactive power control, completing the core objectives of this technical module. We began by analyzing overhead conductor selection, contrasting the industry standard ACSR with advanced ACCC and HTLS technologies for thermal capacity. We then explored the mechanical constraints, applying the parabolic formula W times L squared over AT to calculate sag tension safety margins. For extra high voltage lines, we saw how bundled conductors effectively manage corona loss by reducing the surface voltage gradient. Transitioning to system architectures, we compared LCC and VSC HVDC technologies and examined the thermal rating limitations of underground XLP cables. Finally, we synthesized the necessity of passive reactive power compensation utilizing capacitor banks and shunt reactors to maintain a stable voltage envelope. Mastering these six domains is essential for modern high voltage grid management. Thank you for completing this module on transmission systems. Refer to the technical manuals for specific design parameters and safety standards.